Hello, this is Armand from Team 16397 Relatively Quantum, and today I'll be walking you through the programming and controls used on our robot. Starting with ring detection. One thing we knew would be imperative to successful autonomous this year was detecting how many rings were stacked. Initially, like most teams, we started by using the sample code provided by FIRST that had a pre-trained machine learning algorithm that utilized the TensorFlow library. However, we found that although it was good at detecting whether there was a ring or not, it could almost never tell the difference between a ring stacked with only one ring and a ring stacked with 4 rings. So we added a custom touch to the program. Instead of relying on the built-in detection of single or quad rings, we grouped them both into a general detection of if there were any rings present. And from there, we compared the ratio of height to width of the bounding box around the rings. If it was a high ratio of height to width, then we knew it was 4 ring stack, and if it was a low ratio, we knew it was a 1 ring stack. After a period of 2 seconds, if it was unable to find any rings, neither single nor quad, then we determined that there were no rings. Now that we're able to know what quadrant to go to, we need a reliable way of getting there. Always maintaining a reliable heading was very important for us this year, since we noticed that even a slight deviation in angle would cause rings to shoot and completely miss the narrow opening of the high goal. To ensure that we would have precise turning, we used not one, but 2 gyroscopes, one from each hub, and used their average angle of the 2 readings to calculate our heading as accurately as possible. From there, we used a custom loop that slowly accelerates and decelerates the robot to arrive at the desired angle. Maintaining an angle is important, but so is adapting to your environment. Using sensors that examine the external world is a great way to do this. Thus, we have 2 distance sensors mounted on our robot, one on the side and one on the back. This allows us to dynamically adjust our position depending on the environmental variables, such as distances from walls or a wobble goal. In the example visible right now, the robot is utilizing 2 distance sensors to measure the distance to both perpendicular walls and come back to the same position, even when lifted up. Controlling the robot drivetrain is important, but so is controlling our arm and shooter. To effectively control them, we used a closed-loop PID system, which is imperative for their function. Starting with our arm. The encoder values are tracked in a simple controller where if the arm goes past the encoder position, then negative power is applied, or if it falls behind, positive power is applied. In this way, we're able to hold the arm in positions where it's not able to mechanically hold itself. Additionally, on our shooter, we use a similar system, but this time, it's not used to hold the position of the shooter wheel, but rather track the speed it's rotating at based on the number of encoder ticks we read per second. Based on this, we either increase or decrease the power to get to the shooting velocity you desired. We can now implement these techniques into our autonomous routine. We have 3 unique autonomous routines for boxes A, B, and C, depending on how many rings were detected to be stacked. So, we can quickly speed through each one and talk about it. All autonomous modes start in the same fashion. They all drive up a certain distance, slightly changing depending on the reading from the voltage sensor, and then shoot the 3 preloaded rings into the high goal. From here, all 3 routines diverge slightly. The routine for square A then places the wobble goal inside box A, then backs up into the second wobble goal using the distance sensor at the back to just come in contact with it, and then drags the second wobble goal into square A as well. B is similar. It strafes to align with the B square, then deposits the wobble goal in it. During strafing, the gyroscope automatically corrects the angle of the robot, since when strafing, without preventative measures such as these, the robot tends to drift drastically. It then drives straight to the next wobble goal, again using the distance sensor, turns and picks it up, and then deposits it in square B as well. Finally, C is a little bit different. After shooting the 3 preloaded rings, it'll go back and try to collect 2 more rings from the starter stack. It then shoots these 2 rings before finally depositing the preloaded wobble goal in square C. We also have certain programming features which makes controlling the robot in the teleop period easier. Shooting on our robot, for example, is actually a very involved process. First, the shooter needs to turn on and rev up at the correct speed. And then from there, the ring pusher must extend to push the ring into the shooter wheel, and then retract so that it let the rings above it fall down and allow the cycle to repeat. This process is all abstracted away to a single button press that'll shoot all 3 rings. Another small but useful automation is that the arm has a toggle for extending and retracting at wall height, which uses predetermined encoder positions so that the driver only needs to press one button for the arm to accurately and quickly go to any of the 3 spots. Additionally, the wobble goal gate mounted at the end of the arm also automatically opens and closes depending on the position of the arm, so it can either pick up, hold, or drop the wobble goal. And with that concludes our control award submission. I hope you found the video insightful and engaging, and thank you for your time.